Lack of fit test in Navure version 2.8. When fitting a model that includes covariates, the question is whether the assumption about how the covariates affect the response is correct. In a simple case, when a model includes a single covariate, as in simple regression, the assumption is that the means of the response are ordered on a line that is a function of the single covariate. If the correct model requires the inclusion of a quadratic term, the model may exhibit lack of fit. To test for lack of fit, the model should be refit with the covariates treated as classification factors. In this case, the relationship between the covariates and the response will be as flexible as possible. Comparing this flexible model with the original model provides a test for lack of fit. A prerequisite for using this tool is to have replications for the different values of the regressors. Simply having replications is not always enough. The pattern of appropriate replications will depend on the complexity of the model. Navure will test whether the flexible model can be fitted and return the result of the test or a message that the test could not be calculated. To illustrate this procedure, open the Growing Pasture test dataset in the Test Data repository. It contains 4 columns: treatments, plot, time, and growth. These data summarize the results of an assay in which 5 plots for each of 2 treatments were monitored 9 times to record pasture growth, with measurements taken approximately once per week. To get an idea of what we want to model, we will create a scatter plot of growth versus time, divided by treatments. Go to the Graphics tab, press the Scatter Plot button, select growth as the Y variable, time as the X variable, treatment as the partitioning criteria, and press the Run button, a blue arrow in the upper left corner of the dialog. There are 2 sets of points corresponding to the 2 treatments, A and B, with the points belonging to B, the darker points, above those of treatment A. It is clear the measurement of growth increases on time. A key point, which will allow us to perform a lack of fit test, is that there are replicates of growth values for the different times. Now we are going to fit a regression model including treatments. Since there are several observations on the same plot, we need to include a random effective plot to account for the lack of independence among observations on the same plot. Go to the Univariate tab and press the Mixed Linear Models button. In the Emerging dialog, drag growth to the response variable list, treatment and plot to classification factors list, time to the covariate list, and finally press the Run button. A new dialog will be displayed to let you specify the model components as well as specify different output options. Select treatment and time in the list on the right and press the Interaction button in the Fixed Terms panel. This action will add, to the fixed terms of the model, the effect of treatment, time, and the interaction of treatment by time. This model fits 2 regression lines. Before proceeding, click the Random Terms item in the list at the left. Now double-click Plot in the right list to add Plot as a random term. Finally, click Output TO Report item in the list on the left. Verify that diagnostic graphics are selected, and more importantly for this demonstration, to check the lack of fit test at the right, left corner in the first panel. Now we can proceed by clicking the OK button at the bottom right corner of the window. Although there is a significant interaction of treatment by time, meaning that growth over time varies as a function of treatment, the lack of fit test tells us that the means of growth do not lie on the regression lines we fit. Looking at Figure 1 in the output, it is not so easy to see why the lack of fit is significant, but looking at the standardized residuals versus time plot in the diagnostic plots, the reason for the lack of fit is very clear. If you are familiar with interpreting diagnostic plots, it is quite clear that if you want to stay in the realm of linear models, you need to think in terms of a third-degree polynomial in time. To fit this model, return to the Univariate tab and click the Mixed Linear Models button. The first dialog box, where you select the variables to be included in the analysis, is already filled in, so just click the Run button. In the dialog box that appears, select time from the list on the right and press the square X icon. A dialog will appear asking you to specify the degree of the polynomial. Enter 3 and accept. This action adds new elements to the right list that symbolize time raised to the second and third power. These new elements have also been added to the list of fixed terms. However, since we have a treatment factor that can define different growth curves, we need to add appropriate interactions. Select treatment and the new elements while holding the Control key and clicking on the elements to select. Then click the Interaction button in the Fixed Terms panel. This will add to the interaction terms. Press the OK button. Now the lack of fit test is no longer significant, which means that including the third-order polynomial in time was a good decision. In Figure 1, we can see that the new fitted curves better match the shape of the scatter points. The plot of the standardized residuals versus time looks much better. Since version 2.8, we have also introduced tools for model selection. We can try to see if all terms are necessary for a good fit. The procedures use algorithms to decrease the total number of models that need to be fitted and prevent inconsistencies, such as retaining an interaction term without its corresponding interacting factors or including a powered covariate while excluding the original covariate. To use this tool, return to the Univariate tab and click the Mixed Linear Models button. The first dialog box, where you select the variables to include in the analysis, is already filled in, so just click the Run button. In the dialog box where we specify the model, at the bottom of the Fixed Terms panel, you will find a drop-down menu offering several selection methods. These methods are variations of two primary algorithms, backward elimination and best subset selection. Backward elimination variations depend on the p-value threshold used to remove terms. Best subset selection relies on criteria such as AIC to compare subsets of terms. Let's proceed with best subset selection using AIC as the ordination criterion and click the OK button. While it is a highly effective method, it can become computationally intensive when the number of potential models to evaluate grows too large. The results present the best 3 models ranked by AIC. The first model was chosen for further analysis. In this model, the interactions between treatment and the second and third powers of times were excluded. The lack of fit test remains non-significant. Additionally, Figure 1 and the diagnostic charts show no meaningful changes when compared to those of the full model. Observations. The original model was estimated using restricted maximum likelihood, REML, but model selection methods need to use maximum likelihood, ML, for comparing models with different fixed terms. After choosing a model, refit it with REML if you are interested in random parameters, noting that the ANOVA table will vary by estimation method.